Dr. B here, and let's take a look at some classical identification methods. These always need to be preceded by separation methods because none of these methods are going to work to identify an unknown sample unless it's pure. So you got to put in the work, get yourself a pure sample, and then a good idea if it's a nice high melting solid is check out its melting point. If it's liquid, you might want to check out its boiling point. If you did those two things for an unknown substance and found its melting point was 0 degrees Celsius and boiling point was 100 degrees Celsius, there's a very high likelihood you're talking about water. More modern methods use a little more electronics. What you're looking at here is an atomic absorption spectrometer. And what that does, believe it or not, it's got a big flame inside it, and it will take a pure sample and it will pyrolyze it. Typically, if it's a hydrocarbon, it'll give you carbon dioxide and water. And the flame color shows you the absorption of each element. Carbon, hydrogen, sulfur, they all have a given fingerprint for absorption and a given intensity of that, and these devices can give you an empirical formula, for example H2O, based on that sort of information. Here's an infrared spectrometer, and what that does is it measures the absorption of your substance in the infrared region. Organic substances show a fingerprint within this region and is very diagnostic. Each one of those peaks refers to a certain type of stretching or bending of the bonds, and you can identify a sample usually based on the fingerprint there. Nuclear magnetic resonance spectroscopy is very popular. This is analogous to an MRI, but it's for a substance. Rather than putting a person in, right in there, they put a little glass straw with the sample dissolved in something that does not give an NMR signal, so you end up with only the signals due to your substance. I'm not going to say too much about it since it's a little bit complex, but you do end up with a very good roadmap of your substance. Every one of those peaks shows you where the hydrogens typically are in your molecule and what the neighboring hydrogens are like. So you stick it all together and you get a structure. It's typically done only for hydrogen. It can also be done for carbon and a few other elements. We also have a mass spectrometer, which will ionize your sample and then fragment it and give an idea of its molecular weight. A handy thing to know, 18 for water, 2 H's and an O, 1 plus 1 plus 16 is 18. And then somebody not too long ago had the bright idea to stick these things in tandem. And this is almost like a chemist in a box. So first we put in a LC, which is a liquid chromatograph, and then we attach to that once it separates the substance, since that's a separation device. Each pure substance is then analyzed by mass spectroscopy, and you end up with something like this, a bunch of peaks with numbers on top. Each one is the pure substance in your mixture, at least you hope it is. Occasionally you get overlapping bands and you still have to do further purification. And then it also gives you the mass spectrum of each peak. An extremely powerful device, and is still pretty much state-of-the-art for identifying mixtures these days. This is identification method.